In this video, I'd like to discuss forming a global stiffness problem out of various local stiffness problems. Suppose the domain of my problem, my two-dimensional object, could be represented by this rectangle. Here I have a global nodal numbering system where I've labeled this point node 1, this point node 2, this point node 3, and this point node 4. I've broken my domain up into two triangular elements, element number 1 and element number 2. In the previous videos, I've always labeled my various nodes, node number 1, node number 2, and node number 3. You can think of that as a local node numbering system. It's a little dangerous to do so, but you may think of that way. Remember, I said that it's important that I labeled my nodes numbering in a counterclockwise direction because that's how I derive the form for the global stiffness or for the local stiffness matrix. So if I was going to do that to these two triangular elements here, my first element, I'd have to number my nodes this way. So I would have node number 1, node number 4, and node number 2 forming my three local nodes. I would call this 1, 2, and 3. My local displacement vector, therefore, is going to be of the form u1, v1, u4, v4, u2, v2. And my local stiffness matrix will then, each column will correspond to what's going on x1, y1, if you prefer u1, v1, x1, y1, x4, y4, and x2, y2. The three surface forces will the three force components, body, surface, and point forces, each component of those 6x1 vectors will all get added together or summed together for a total equivalent force at the nodes for x component, y component for each node. So I will have, and now I'll just get rid of the subscripts, I will have a force 1 in the x direction, a force 1 in the y direction, a force 4 in the x direction, a force 4 in the y direction, a force 2 in the x direction, and a force 2 in the y direction, each coming from element 1. I'll use that as a superscript. My second element, I can label my local nodes. Let's see, I'd be have to go counterclockwise. So I will go from 2 to 4 to 3. I will get a local stiffness matrix, a local displacement vector. My local displacement vector will now be, let's see, I'm going 2, 4, 3. I'll have u2, v2, u4, v4, u3, v3. Likewise, along the top, each column to label the tops of my columns, I could think of this as x2, v2, y4, this would be y, x3, y3. My local force vector will now be f2x, f2y, f4x, f4y, f3x, f3y. Now that I have my local problems, I can now form my global stiffness matrix and my global force vector. My global stiffness matrix, since I have 4 nodes and I'm solving for x and y displacement at each node, will be an 8 by 8. So I will get an 8 by 8 matrix. Now I'm in the global system. I want this to be labeled 1, 2, 3, and 4. So along the top, I will label the columns of this matrix x1, y1, x2, y2, x3, y3, x4, y4. As I place the various and sum up the various members of these 2 matrices in here, I will want to place everything in an xi column here, in an xi column here, and everything in a ui or a vi row here, in a ui or vi row here. My global displacement vector will, of course, be u1, v1, u2, v2, u3, v3, u4, v4. To form my global force vector, I need to sum up the corresponding components of the forces here and the forces here. These are all the components from the first element. These are all the components of the second element. I should label that with superscripts here. So to form my global force vector, I have F1, Y1 from the first element, F1, X, F1, Y from the first element. I have F4, Y4, F4X, F4Y from the first component. I have F2X, F2Y from the first component, F2X, F2Y from the first component. There's nothing in the first element involving the third node, so this will be 0, 0. I will then add forces affecting these nodes due to the second element. So I'll have F2X, F2Y due to forces acting on the second element, F4X, F4Y due to the second element, and F3X, F3Y due to the second element. I can also think of these globally as capital F1X, capital F1Y. This would be capital F2X, capital F2Y, these 2 terms added together. This is not that dissimilar from what we've done in the one-dimensional bar and beam case. All right, that wraps out this lecture. In our next lecture, we'll just start discussing rectangular 2-dimensional elements.